This is Jason McIntosh with McIntosh Applied Engineering. In this video, I'm going to take you through using the graph element in the Acoustic Modeler module. I'm going to start with an existing model that I've already put together. This model doesn't have a graph element yet. To solve the model, you can press the Calc button or the F5 button. Once you solve the model, each node, shown in red here, will contain solution information. For the acoustic elements, it's going to be the pressure and volume velocity at the acoustic nodes. And for the electrical nodes, it'll be the voltage and the current at each one of the nodes. To get the information out of the model, you use the graph element. The graph element is found under the miscellaneous directory. When you create a graph element, a graph window is automatically created. This window doesn't have any information in it yet because we haven't connected the graph to one of the nodes. To view the information at a node, run a connector from the graph element to the node where you want to display the information. When we do this and we bring up the graph window, we now see the pressure plotted at that point. Had this been an electrical node, we would have seen the voltage plotted. Note that this curve is called the current buffer. The graph element has 27 buffers that it stores information in. When you connect a graph element to a node, it copies the information from that node into the connector node buffer. And when you plot it, it's given the name current buffer. There are 26 other buffers labeled A through Z that you can access through these three buttons in the graph element's controls. If you type a string into the buffer's text field, it'll become the label for that curve. So I'm going to change the name of the connector node buffer to my buffer, and if I hit enter or press the update graph button, that change will take effect in the graph, and that curve is now called my buffer. I'm going to go ahead and delete that, and we'll stick with the default name for that buffer. There are 26 other buffers, again A through Z, and we can copy the data from the connector node buffer into one of the other buffers by pressing that buffer's letter button. So if I press the A button here, that will have copied the data in the connector node buffer into the A buffer, and now I can call this radiated pressure because that's where we're at. We're plotting the radiated pressure from this radiation element. And I can plot that in the plot by checking the box for that buffer. If I now go back to the graph, there are two plots on this graph. One's called current buffer, and then there's the A buffer, which has the label radiated pressure, but those curves are right on top of each other, so we're only seeing one curve. I can now go back to the model and move the graph connector to the back of the speaker. When I do that, it copies information at this node into the current buffer, and that's what will be plotted in the graph. So now the blue curve is the current buffer, which is the pressure to the rear of the speaker. Buffer A is still being plotted. It's shown in green, and it's labeled the radiated pressure. So we've got two pressure curves now, one representing the pressure at a distance, and the other is the pressure behind the speaker. You can copy the current node buffer into any of the 26 buffers and graph them in the graph window, allowing you to plot many simulation conditions simultaneously. Note under quantity, the graph element controls allow you to plot a number of different quantities based on the type of data in the first buffer that's being plotted. Since we've copied acoustic data into these buffers, we have acoustic data available for plotting. These are the pressure, volume velocity, impedance, force, particle velocity, and displacement. Depending on the information you want, each one of these quantities can be important. Impedance is important to understand the load that the speaker drives. Particle velocity is important in understanding nonlinearities that may occur. For acoustic processes, usually particle velocities above 1 meter per second indicate that nonlinear effects may be present. Displacement is important, particularly for moving coil speakers. Moving coil speakers will behave nonlinearly at high displacements. Whether you're plotting a linear log x, log y, or log-log plot can be selected under the Type drop-down box. Typically for audio processes, we'll use a log x graph as the hearing system operates on a logarithmic frequency scale. But sometimes it's interesting to see the data on a linear scale. This doesn't look like what we're used to, but this scale can still be important, particularly if we're looking at modal effects, which are best looked at and understood on a linear scale. I'll get to the versus iterator and normalize to features later. And I'm going to change this back to a log x scale. The x-axis range field allows you to specify the x starting and ending values. So if I enter 200 and 5,000, it'll change the x-axis scale to be from 200 Hertz to 5,000 Hertz. Same with the y-axis. I can enter a value of 50 to 100, and that's now what the y-axis will be plotted with. If you only enter one value, the first value will be taken as the minimum value for that axis, and the maximum value will be auto-scaled. You can create as many graph elements as you'd like. In this case, I'll create a graph element and I'll plot the voltage at the speaker terminal. This is the graph window that was created. Now we've got two graph windows and things can get a little messy. If you delete a graph element, it will delete the graph window and all the data stored in that graph element as well. But if you simply don't want a graph window to be plotted, you can select the hide graph feature and that window will then disappear until you turn it on again by unchecking hide graph. Note that with this other graph, the quantity type is electrical. You can plot voltage, current, impedance, and charge. If we select impedance, we see a typical impedance curve into a moving coil speaker. I'm going to delete this second graph element just to unclutter our model. The Set Buffer Line button brings up a dialog box that lets you provide information about how you want each curve to be plotted. You can select the line type, solid, dashed, etc. You can select the line weight from 1 to 6, and you can specify a mark type. Each buffer can have its own unique type, weight, and mark. For most modeling exercises, I'll leave the line weight to 1. But when exporting the graph to be plotted in a program such as PowerPoint, I'll usually increase the line weight to something closer to 3. Note that the graph element is updated immediately. So now our current buffer has a line weight of 3, and the A buffer has a line weight of 1. If you want to change the line weight of all of the buffers, you can press the Set All button, so you don't have to manually go through each buffer. Here I'll click Set All. I'll go back to the graph, and now the A buffer is also having a line weight of 3. When you have a lot of curves on the graph, sometimes setting the mark type is also useful to help your data stand out. I'll set these back to the default values. I'm going to go back to the radiated pressure. I'm going to uncheck A, and now I'm going to iterate on the back volume diameter. When you iterate on a parameter, you get a family of curves, which essentially creates a sensitivity plot. Note that all of these curves are currently being stored in the current connector node buffer. But if we copy them to buffer B, I'll label this iterated pressure and plot B. I'm going to turn A off. You'll note that buffer B contains all of the iterated curves. So if you want, you can store different iteration results in the buffers as well. I'm going to perform a single calculation to remove the iteration results from the connector node buffer. I'm going to go to set line buffer, and I'm going to make sure they're all a line weight of 1, except I'm going to change the first buffer to a line weight of 3, press OK, and now we have the current buffer, which has a single curve in it because we pressed the calculate button without the iteration feature, and buffer B, which contains the iteration results, so we can see where our current design is relative to our iteration values. I'll turn buffer B off now and go back and set the line weights to 1. To show the versus iterator and normalize to features, I'm going to create a new module. Go to the new modules menu, select modeler, and I'm going to create a directional microphone model. I'm going to excite it with a plane wave source. I'm going to connect them up. I need to ground one terminal of the microphone. And now I'm going to create a graph element and connect it to the microphone. If I hit calculate, this is the graph it generated. It's a voltage response from the microphone. And it's showing a typical low frequency roll-off that you see with directional microphones. The plane wave source allows you to specify the direction that the plane wave is arriving from. Its default value is 360 degrees. If you look at the plane wave's help text, it'll tell you that 0 degrees, or equivalently 360 degrees, is a wave traveling from the left to the right. What I'm going to want to see is the polar response of this microphone at all the angles from 0 to 360 degrees. To do that, I'm going to iterate on the angle value. But first, I'm going to need to change the iteration range in global parameters. I'm going to have it start at 0% of the current value, and I'll have it go to 100%. So when I iterate on the angle, I'll essentially iterate from 0 to 360 degrees. And I want a lot more than 5 iteration steps. I'm going to select 37, which will provide an iteration every 10 degrees. So if I go back to the plane waves parameters and iterate on angle, I generate this set of curves. This is pretty intimidating to try to understand what's going on here. But what we can do is we can plot slices through this data at specific frequencies and plot them versus the iterator, which is going to be the angle. To do that, I'll go back to the graph element and I'll tell it I'm going to plot versus iterator at, and I'll choose some frequencies here, 500 Hertz, 1000, 2000, 4000, and I'll select versus iterator. If we go back to the graph, I see something that doesn't look very nice because our x-axis is on a log scale. I'm going to go back and change the type to linear. And now this makes a little more sense. We're seeing the angle plotted from 0 to 360 degrees. Ares does not have a polar plot, so this is as close as we get to seeing polar type data. 0 degrees is on the left, 360 on the right, and you can see that there's a large null at around 180 degrees. So this is implementing something like a cardioid microphone. However, usually when you plot polar responses, you want to normalize the levels at 0 degrees to 0 dB. We can do that by using the normalize to feature. Here, if I check this, it will normalize the y value for each curve to be 0 at x equals 0. You can enter whatever parameters you want in here, but these work well for our polar data. Checking this and going back to the plot now shows our polar type data normalized to 0 dB, and we can easily read off the fact that we're getting a null between 15 and 20 dB at 180 degrees. So that's a quick example of how the versus iterator and normalized to features can be used. But you can get creative and find other useful applications for them in your modeling efforts. I'm going to go back to the original model we created. It just shows the radiating speaker. The last control in the graph's control list is the bring graph to top. When you have a lot of windows on your screen, it can be hard to find the graph window sometimes. Things can get kind of cluttered. To bring that graph window to the top so you can easily see it, just press this button and the graph window will pop up. You'll find that you use this feature fairly often if you have a lot of windows on your screen open at one time. Not all of the graph features can be displayed in the left panel on Ares. All the other features are available in the Advanced Options dialog box. By default, the graph elements will show the magnitude of the data in the buffer. However, you can also plot the data as real and imaginary, phase, power, which is going to be pressure times velocity, or current times voltage. Leak tolerance is a special feature that allows you to show the difference between sealed, high leak, and low leak ear simulation results. And the time response is just the FFT of the data. But here I've selected magnitude, real and imaginary, and phase. And I'll show you what that graph looks like for the pressure data that we're plotting. Real and imaginary parts are mostly useful for plotting impedances, and I find phases important when you're developing an active noise control system and you want to ensure the stability of the feedback control. Normally, the magnitude data will be plotted in dB, but you can select linear if you'd like, or you can plot dB in full octave bands or third octave bands. If I select linear, we'll see the pressure plotted in pascals instead of dB SPL. If I select full octaves, we'll now see the power in each of the full octaves being plotted. Ares assumes an RMS source for all of the sources. By selecting peak level, you basically increase the levels by 3 dB. You can control the legend features here. If you enter text for a given buffer, normally the buffer letter is no longer plotted in the legend. However, by selecting Show Buffer Letter, you can force the buffer letter to be displayed. Let me go back and have the buffer A selected for plotting. So now A is appearing in the legend entry for that buffer. The legend can be auto-positioned every time, which is mainly going to put it up in the upper right corner. Or you can tell it to use the fixed position wherever you've left it, so it won't move around every time you update the plot. Or you can tell it to get rid of the legend altogether. You can shift the data magnitude in a buffer by using the Shift Buffer Data by dB value feature. Here I'll select buffer A and I'll tell it I want to move the data down by 10 dB, so I'll enter -10. If I hit apply and go to the graph, My A buffer now has been moved down 10 dB. This can be useful if you want to offset curves just a little bit to differentiate them, or if your data needs to be normalized by some quantity for some reason. dB is just a magnitude effect, but if for some reason you want to change the sign of the data, you want to invert its phase, you can apply the shift with the invert phase option checked. I've found this feature most useful if I'm importing data from the frequency response module and the polarity between my microphone and my speaker are off by 180 degrees. I can correct for that here in the modeler module instead of going back and retaking the data. The graph element has the ability to compute metrics for each one of the curves. These metrics are defined in the manual, and I'll refer you to them for more details. But just by checking some of these and going back to the graph, you'll find that each curve has some metrics being reported after the legend entries. There are some other features available at the bottom of the dialog box. These allow you to apply A weighting, B weighting, C weighting, P50 speech weighting, that's from the ITU P50 specification, phosphometric weighting, that's a noise weighting. These weighting functions can be individually applied to the connector node and all of the other graph buffers. So we end up with rather a complicated matrix of options listed here. If I go back and I shift the data for the A buffer back up, so it's now essentially equal to what's in the current buffer, and I select A weighting for the A buffer, we can see the effect of applying A weighting to our data. Note that the A buffer now is being plotted differently from the current buffer. Using the plot negative kinetic energy value option is most useful for plotting impedances. An impedance is defined as the ratio of the pressure divided by the volume velocity at a given point. However, the volume velocity is always defined to be into a node. So if we plot the impedance at the back of the speaker, we're going to see the impedance seen looking into the speaker, not the impedance seen looking into the volume. The pressure at the volume and the back of the speaker are the same because they're connected together, but the velocities have opposite polarity. So if I go ahead and plot the impedance of the volume, I'm going to turn A off, select impedance. I'm going to select the plot real and imaginary and go back to our graph. We see the real and imaginary parts of the impedance into the volume in the lower graph. Note that the imaginary part is negative and following a 1 over j omega curve, which one would expect for a volume. But if we now take the graph connector and we connect it to the back of the speaker, the impedance now has a positive imaginary part, and it's going to positive infinity. This is the negative of impedance that we would really like to see. To correct for this, the Advanced Graph Options dialog box has the option to plot using a negative kinetic value. By checking that for the current buffer, we now invert the sign for the impedance. And so now we have an impedance that we would expect to see looking from the back of the speaker into the load that it's driving. The Advanced Options dialog box also has two menus in the upper left corner. The File menu allows you to import and export data from one of the buffers. If we export data from the current buffer, we can save it in a text file format. Here I'll select a current existing file. Then if we go back and we try to import the data, Ares will ask us to specify what type of data that we're loading in. So you can create your own text files and load your own data in. You can also import fixed and floating mask responses. I'm going to import a floating mask into buffer D. Ares comes with a masks subdirectory, which contains some common masks found in the telephony industry. I'm going to select the CDMA mask. I'm going to stop plotting the real and imaginary part. I'm going to select the mask for plotting. When I bring up the graph, it doesn't look quite right because we're still plotting impedance. So I'm going to select pressure, bring the graph back up, and now our CDMA mask is trying to be fit to the pressure response as good as possible. Since this is the pressure behind the speaker, it doesn't look very good. I'm going to select the pressure in front of the speaker again, which is a little flatter, and the mask has a little easier time being met. Ares will do its best to fit the mask to the first curve that's being plotted. When your mask has a pinching effect, it'll only fit it at the one frequency where the upper and lower curves come together. If I load a different type of mask, which doesn't have the pinching effect, Ares will match the response over the entire range as best as it can. When you import a fixed mask, you have to manually shift it around to get it to match your data. So I'm going to select the GSM mask, import it as a fixed mask, and it's now way down by 0 dB. To move that up, I've got to go to the advanced options, select my fixed mask buffer, and start moving this up a little bit at a time. So I want to move it up about 70 dB. So I can do 10 dB 7 times. 1, 2, 3, 4, 5, 6, 7. Should have moved it up about 70 dB. And so we're about where we want to be. And you can continue to manually adjust it using the shift buffer feature. The edit menu allows you to copy data to the clipboard. It'll copy it in text format. If you hold the control key down, the text format will be appropriate for MATLAB. Otherwise, it'll be in tab delimited columns, most useful for Excel. So I'll go ahead, I'll hold control down, select current buffer. I will open a MATLAB screen. And I'll just paste the result in the MATLAB. The result is a data structure called data. Has fields data.frequency, data.p. Note that these values are complex. So if I want to plot that, I can type in semi-log x, data.frequency, comma, and I have a function called JSPL, and I'll pass it the pressure, data.p, grid on. That'll create a graph in MATLAB, and so now we've exported our data to MATLAB using the edit function in advanced options dialog box. You can also paste data in using the clipboard. If I wanted to generate some sample data, I can open a notepad, hold that over, and just type in some simple data. I'll do 500 will be 80 dB, 1000 will be 100 dB, 2000, will be 110 dB, 5000 will be down to, say, 50 dB. I'll copy this to the clipboard, select Edit, paste buffer from clipboard. I'll select buffer H, and I'll indicate that it's going to be frequency and SPL, first option, So if I select H for plotting now, turn the GSM mask off, we can see our fictitious data that we entered in from the clipboard. That wraps up the graph element features, but before we leave, I wanted to show you some features of the graphs found in Ares. If you bring up a graph and you right-click on it, you'll find a menu. This menu is the same across all graphs in Ares, whether it's a graph element graph or whether it's from a data acquisition graph. It allows you to copy the data out for individual curves. You can copy the data from all the curves simultaneously. You can copy the graph. You can zoom in to different parts of the curves. You can auto scale out. There's also a help feature that tells you a little bit more about how you can interact with the graph. You can use the wheel to do some auto panning in and out. Hold the control key down and you'll shift left and right, etc. Copying the entire graph to the clipboard, you can paste it into a program such as PowerPoint. I'll paste it in, and here's a graph ready for documentation. Well, those are all the features of the graph element. I hope that was informative. Thank you for your patience and all the time you spent watching this. The graph element is really a critical element in the modeler module. It's where you display and interact with all the data from your model. So using it well and efficiently is really important. If you have any questions, please feel free to contact us at support@maellc.com.